Imagine you are falling, not stumbling on a sidewalk, not tumbling from a ladder, but falling through space itself, through a boundary so absolute, so final, that the universe you have always known simply ceases to apply on the other side. You are falling into a black hole. And here is the extraordinary thing: you would not feel a thing, not at first. The stars would still shine above you, time would still tick, at least by your own watch. And yet, from that moment forward, every possible future you could ever have would point inward, only inward, toward a point of infinite density from which not even the geometry of space can escape. What happens to you? What happens to information, to matter, to the laws of physics themselves? These are not science fiction questions. These are the deepest, most unsettling questions in all of modern physics, and the answers, astonishing as they are, begin with a theorem, a diagram, and a mind that decided to ask what happens when mathematics meets the end of everything. Let us begin not in space, but in thought. The universe is not simply a collection of objects floating in emptiness. It is a fabric, a four-dimensional weaving of space and time that bends and warps wherever mass and energy are present. This was the great revelation of general relativity, published by Albert Einstein in 1915. Gravity, Einstein told us, is not a force pulling objects together the way a magnet grabs iron filings. Gravity is the curvature of space-time itself. A massive object warps the fabric around it, and other objects simply follow the straightest possible path through that curved fabric. We call those paths geodesics. The Earth follows a geodesic around the Sun. Light follows a geodesic through curved space-time near a massive star. And when that curvature becomes extreme enough, when it becomes so severe that geodesics bend not outward but only inward, you have a black hole. But Einstein himself did not believe black holes could actually exist. He thought the mathematics predicting them was a curiosity, perhaps an artifact of the equations being pushed beyond their domain of reliability. The singularity, that point of infinite density at the center, was surely, he believed, a mathematical fiction, not a physical reality. Surely nature would find a way to prevent such an extreme object from ever forming. And for decades, many physicists agreed with him. Then came a young mathematician who was not willing to accept that assumption. He was sitting in a train, traveling between two cities, turning over an abstract problem in pure mathematics, topology, the study of properties that persist when shapes are stretched or deformed, the study of what cannot be undone, and he began to wonder, what if you could apply topological thinking to the equations of general relativity? What if instead of asking whether a particular exact solution behaved in a particular way, you asked a broader question? What must happen necessarily, inevitably, given only the most basic and well-tested assumptions about how gravity works? This shift, from specific calculations to necessary consequences, was the conceptual revolution, and the result was the Penrose Singularity Theorem published in 1965, which proved with mathematical certainty that once gravitational collapse proceeds beyond a certain point, a singularity is not merely possible. It is inevitable. Not contingent on special initial conditions, not dependent on perfect symmetry, not an artifact of idealization. Inevitable. Given only that gravity is attractive and that a certain geometric condition is met, the existence of what is called a trapped surface, the laws of general relativity themselves guarantee that geodesics will converge, that space-time curvature will increase without bound, that a singularity must form. Let us understand what a trapped surface is, because this concept is the engine of the entire argument. Ordinarily, when you emit a flash of light in empty space, the light expands outward in all directions, forming an expanding sphere. That is simply what light does in flat spacetime. Even near a moderately massive object, light can still escape if it is moving away from the object. But imagine you are deep inside a region of extreme gravitational curvature, so deep that even light moving directly outward is actually moving inward relative to the distant universe. Even the outward-pointing light rays are converging rather than diverging. A surface with this property, where all future-directed light rays converge inward regardless of direction, is called a trapped surface. And the singularity theorem states, once a trapped surface exists, a singularity is unavoidable. This is a profound statement. It is saying that the geometry of spacetime itself, once sufficiently curved, is self-amplifying. The curvature causes convergence, the convergence increases curvature, and the process runs away without limit, reaching a terminus that is not a place in space but a boundary of spacetime itself, a point or a set of points where the mathematical description of the universe simply breaks down. A singularity. Now let us think carefully about what it would actually be like to fall into a black hole, because the subjective experience depends very sensitively on where you are and what kind of black hole you are falling into. Consider first the stellar mass black holes and the remnants of massive stars that have exhausted their nuclear fuel and collapsed. These objects have masses of perhaps 10 to a few tens of times the mass of our Sun, compacted into a region only a few kilometers across. The boundary of a black hole and the surface of no return is called the event horizon. For a stellar mass black hole, the event horizon is a sphere perhaps 30 kilometers in diameter. If you were falling towards such an object feet first, the gravitational pull on your feet, being closer to the singularity, would be enormously stronger than the pull on your head. This difference in gravitational force across the length of your body is called a tidal force, and near a stellar mass black hole, these tidal forces would be lethal long before you reach the event horizon. You would be stretched vertically and compressed horizontally in a process that physicists, with characteristic dry humor, call spaghettification. You would be drawn out into a long, thin strand of matter, atoms separated from atoms, nuclei pulled from electrons, and the entire ensemble accreted toward the singularity in a stream of superheated plasma. But now consider a supermassive black hole. These are the giants that lurk at the centers of galaxies, objects with masses of millions or billions of times the mass of the Sun. The one at the center of our own Milky Way galaxy, known as Sagittarius A star, has a mass of roughly 4 million solar masses. Others, in more distant galaxies, have masses measured in billions of solar masses. For these objects, the event horizon is not 30 kilometers across, but millions or even billions of kilometers across. And here is the remarkable consequence. The tidal forces at the event horizon of a supermassive black hole are actually quite gentle. The horizon is so large, so far from the singularity, that the difference in gravitational pull between your head and your feet at the moment of crossing would be barely perceptible. You could, in principle, cross the event horizon of a supermassive black hole without any local physical experience to mark the transition. No alarm would sound. No physical barrier would stop you. No special sensation would signal that you had just crossed a boundary from which return is forever impossible. This is one of the most disorienting facts in all of physics. The event horizon is not a physical surface. It is not made of anything. It is a boundary defined not by local physics but by global geometry, specifically by which regions of space-time can send light signals to the distant universe and which cannot. From your local perspective, as you fall through the horizon, the laws of physics remain perfectly normal. The equivalence principle, one of the foundational principles of general relativity, guarantees that a freely falling observer in a gravitational field is locally indistinguishable from an observer floating in empty space with no gravity at all. Locally, you feel nothing at the horizon crossing, and yet, globally, everything has changed. From the moment you cross that boundary, every geodesic available to you, every possible path through spacetime consistent with moving at or below the speed of light, points toward the singularity. You cannot turn around. You cannot accelerate away. You cannot fire a rocket and escape. The future in the interior of a black hole is not a direction in space, it is a direction in time. Just as you cannot move backward in time in ordinary spacetime, inside a black hole you cannot move away from the singularity. The singularity is in your future, not in a particular direction in space. This is what the trapped surface theorem captures geometrically. Inside the horizon, all of spacetime is tilted so severely toward the singularity that forward motion in time is forward motion toward the end. How long would it take to reach the singularity after crossing the horizon? For a stellar mass black hole, the answer is microseconds. For a supermassive black hole of 10 billion solar masses, perhaps a day or so of proper time, time as measured by your own watch. During that time, you are not falling in the ordinary sense. You are simply existing, moving through time, in a region of space-time where the future happens to include a singularity. And as you approach that singularity, the tidal forces grow. Even in a supermassive black hole, the singularity itself is a place of infinite curvature, and in the final moments the stretching and compressing would become infinite. Now here is where the physics becomes philosophically breathtaking, because the singularity theorem proves that the singularity exists, but it does not, cannot, tell us what happens there. General relativity predicts its own failure at the singularity. The equations produce infinities, infinite curvature, infinite density, and in physics, when your equations give you infinity as an answer to a physical question, that is not an answer. It is a signal that your theory has been applied outside its domain of validity. The singularity is where general relativity breaks down, where quantum mechanics must come into play, where a theory of quantum gravity, which we do not yet have in complete form, is required to describe what actually happens. So in a very real sense, the singularity is not the end of a physical story. It is the beginning of an unsolved problem. It is the place where our deepest understanding of the universe hits a wall, throws up its hands and says, "We do not yet know what happens here." This is why the singularity theorems were not merely a technical result, but a watershed moment in theoretical physics. They told us definitively that we were missing something fundamental. They made the incompleteness of our physical theories not a philosophical worry, but a mathematical certainty. Let us now turn to a related and even deeper puzzle, one that has occupied theoretical physicists for the past half-century and remains unresolved today. It is called the black hole information paradox, and it begins with a discovery made by Stephen Hawking in 1974. Hawking showed that black holes are not entirely black. When you treat the event horizon of a black hole using the mathematics of quantum field theory, applying quantum mechanics to the fields that exist near the horizon, you discover that the intense gravitational field at the horizon causes pairs of particles to be created from the quantum vacuum. One particle falls inward across the horizon and one escapes to infinity. This escaping radiation is called Hawking radiation, and it carries energy away from the black hole. As energy is carried away, the black hole slowly loses mass. Over an astronomically long period of time, for a stellar mass black hole, longer than the current age of the universe by many orders of magnitude, the black hole radiates away all its mass and disappears entirely. This is remarkable enough in itself, but the deeper question is, what happens to all the information that fell into the black hole? Everything that ever crossed the horizon, the atoms of every star that formed it, every particle of gas that was accreted over billions of years, every photon, every quantum of every field, all of that carried information. It had a definite quantum state. The fundamental principle of quantum mechanics states that information cannot be destroyed, that the universe evolves in a way that preserves, in principle, the complete information about its initial state. This is called unitarity, and it is one of the foundational pillars of quantum theory. But if the Hawking radiation is, as Hawking initially calculated, perfectly thermal, if it carries no information about what fell in, no subtle correlations encoding the detailed quantum state of the infalling matter, then when the black hole finally evaporates completely, that information is simply gone. The universe began in a state with definite information, but it ends in a state where that information has been destroyed. This violates unitarity. It is not just a practical problem of our inability to recover the information. It is a fundamental inconsistency between general relativity and quantum mechanics. This paradox, does the information escape, and if so, how and when, is the central unresolved problem at the intersection of gravity and quantum theory. It has generated an enormous body of theoretical work. The Bekenstein-Hawking entropy formula, which assigns an entropy to a black hole proportional to the area of its event horizon, suggests that the information is somehow encoded in the geometry of the horizon itself, and perhaps encoded in subtle correlations in the Hawking radiation that are not visible in Hawking's original calculation. The holographic principle, pioneered in work on string theory and the ADS-CFT correspondence, suggests that the entire physics of a region of space, including its interior, can be encoded on a lower dimensional boundary. That in some deep sense, the three-dimensional interior of a black hole might be equivalent to a two-dimensional quantum theory on the horizon. These ideas are astonishing in their ambition. They suggest that the geometry of space is not fundamental, that space itself may be a kind of emergent phenomenon, arising from the entanglement structure of a more fundamental quantum description. And this brings us back to what happens to you inside the black hole. If information is preserved, if unitarity holds, then the Hawking radiation must be encoding information. And the question of how it does so, given that the horizon is locally perfectly ordinary, given that the equivalence principle says nothing dramatic happens there, leads to a confrontation between different principles that we have always assumed were separately valid. Something has to give. Either information is destroyed, violating unitarity, or there is some dramatic physical effect at the horizon, violating the equivalence principle. Or our understanding of locality and quantum gravity is fundamentally wrong, and the correct resolution requires a conceptual framework we have not yet constructed. The firewall paradox, proposed in 2012, sharpened this conflict to a fine edge. It showed that if you insist on unitarity, on information being encoded in the Hawking radiation, then the entanglement structure of the radiation necessarily implies a disruption of the smooth geometry at the horizon. An infalling observer would not cross an empty, unremarkable horizon. They would encounter a wall of high-energy radiation, a firewall that would destroy them instantly. This seems to conflict with the equivalence principle, and the community of theoretical physicists, upon seeing this argument, did not immediately resolve it. They recognized it as a profound puzzle revealing genuine tension in our assumptions. The resolution, whatever it turns out to be, will almost certainly require a theory of quantum gravity that is more complete than anything we currently possess. It may require revising our understanding of what it means for events to be localized in spacetime. It may require revising the holographic principle. It may require understanding the geometry of spacetime as emerging from quantum entanglement in a way that fundamentally alters how we think about space and information. What is extraordinary about all of this, what makes the physics of black holes so intellectually rich, is that it connects, in a single object, the deepest open questions in all of physics. The singularity connects to quantum gravity. The event horizon connects to thermodynamics. The Hawking radiation connects to the foundations of quantum mechanics. The information paradox connects to the nature of space and time themselves. A black hole is not just an exotic astronomical object. It is a laboratory, a theoretical laboratory, in which the consistency of our entire physical worldview is tested to its breaking point. The tools that revealed this, the tools of global geometry, of causal structure, of topological arguments about the behavior of geodesics, these were not developed to study black holes specifically. They were developed to answer a fundamental mathematical question. Given that Einstein's equations have certain properties, what must inevitably follow? The power of that approach, of proving necessary consequences from minimal assumptions, transformed theoretical physics. It gave physicists a way to reason about the universe, not just by solving equations in specific cases, but by proving theorems about what all solutions must share. The Penrose diagram, a way of depicting the causal structure of spacetime by compressing infinite distances and times into a finite picture while preserving the essential geometry of cause and effect, became one of the most powerful tools in theoretical cosmology and quantum gravity. With it, you can see at a glance which parts of spacetime can communicate with which other parts, which regions are forever inaccessible, where singularities lie, and what the global structure of an entire universe looks like. These diagrams encode in a small square or triangle the entire history and fate of spacetime geometries that would otherwise take pages of equations to describe. The Penrose diagram of a black hole formed by gravitational collapse shows the infalling matter, the formation of a trapped surface, the event horizon growing outward at the speed of light from the moment the first trapped surface forms, and the singularity lying in the future of all observers inside the horizon. The diagram makes visually clear what the mathematics proves, that the singularity is not a place in space that you approach and could in principle avoid. It is a moment in time that every infalling observer must eventually reach. Space and time have exchanged their roles inside the horizon. The radial coordinate has become time-like, and time has become space-like. The singularity is as unavoidable as tomorrow. Now return once more to the question with which we began. You are falling into a black hole. What happens? At the level of classical general relativity, ignoring quantum effects, the answer is this. You cross the horizon without any local alarm, you continue falling, and in a finite proper time, you reach the singularity, where the equations of general relativity cease to be valid. Whether the singularity destroys you in some specific physical way, or whether quantum effects resolve the singularity into something else entirely, a bounce, a transition to another spacetime, something we have not yet imagined, is a question that the physics of 2025 cannot fully answer. At the quantum level, incorporating the Hawking effect, the information paradox, the firewall arguments, the answer becomes genuinely uncertain in a deeper way. Perhaps you encounter dramatic quantum effects at the horizon. Perhaps the smooth spacetime you expected is replaced by something fundamentally different at the Planck scale, at the scale of 10 to the power of minus 35 meters, where quantum fluctuations of geometry are of the same order as the geometry itself. Perhaps the interior of the black hole that you experience is in some sense complementary to the same physical information described in a different way as the exterior view of a gradually evaporating black hole radiating away its mass over astronomical timescales. What is certain is this: the question itself, the question of what happens inside a black hole, is not merely a thought experiment. It is a probe of the deepest structure of physical reality. The tools used to prove that singularities must form are the same tools used to map the causal structure of the entire universe, past, present, and future. The entropy formula for black holes suggested, a decade before anyone realized it, that information is somehow encoded in geometry. The information paradox, still unresolved, is pushing physicists toward a view of spacetime as emergent, as arising from something more fundamental: quantum entanglement, quantum information, a structure not yet fully named. Every time you look up at the night sky and imagine one of those distant points of light as a stellar remnant collapsing under its own gravity, you are looking at a laboratory where the most fundamental questions in physics are being enacted in silence, at scales ranging from the subatomic to the cosmological, in regions of space-time where time itself bends back on itself and the ordinary machinery of cause and effect reaches its limits. The universe is not merely vast, it is not merely ancient, it is, in the most precise mathematical sense, incomplete, containing within it structures that exceed the explanatory power of every theory we have so far constructed. And that is not a cause for despair, it is an invitation. The singularity theorems did not close a question, they opened one. They made explicit, in the language of pure mathematics, exactly where our understanding breaks down and exactly what kind of new understanding is required. The information paradox does the same. These are not failures of physics. They are physics at its most alive, identifying with complete precision what we do not yet know and pointing toward the territory where the next revolution in understanding must lie. The black hole is where general relativity meets quantum mechanics, and the two theories look at each other across an event horizon and realize that one of them, or perhaps both of them in their current forms, must be incomplete. Whatever emerges from that confrontation will change not just our picture of black holes, but our picture of space, time, information, and the nature of physical reality itself. That confrontation is not a historical event that happened in the past. It is happening right now, in equations being written, in theorems being proved, in Gedanken experiments being turned over in minds that are willing to follow the mathematics wherever it leads, however strange, however far from ordinary intuition, however deeply into the unknown.